My name is Helge Eichhorn. By day, I'm a PhD student at the Technische Universität Darmstadt, and I do research in model-based engineering at the Department of Computer Integrated Design. By night, on the other hand, I support the mission analysis section at the European Space Operations Center as an external consultant. And you can find me on GitHub. That repository there is still empty, but after the talk I will upload the slides and the notebooks. So, what is the perfect programming language for astrodynamics? We need performance, so especially numerical performance in iterative algorithms. Nice math syntax would be good, and also well, since astrodynamicists have been programming for a long time, legacy code support would be a plus. So what language could it be? Of course, you all anticipated the answer. It is Fortran 77. Or is it? So unfortunately, this is still true for many organizations. So many organizations in astrodynamics still use Fortran 77. And I think one of the reasons for that is because it all started so early. So computational astrodynamics has been around for a long time. And of course, in the beginning of the space programs, computing costs were the limiting factor. So efficiency was most important. In 2016, this is a whole different story. So usability should be most important. And as we all know, in the last years and decades, we couldn't have both. So when the first public version of Julia was published and I read the blog post, I said, yes, that's it, I need that. And I tried it, and then I didn't use it, which was probably good for my academic career because there were some parts missing, and when I would have gotten started with that, I probably wouldn't have finished my university project. So, but I kept it in the back of my head. I had some success with Python in recent years, and at least one person here in the audience has seen my talk at EuroSci last year about astrodynamics with Python. So. Why Julia instead of Python? Well, when you think back, I said we need performance, we need math syntax, and legacy code support. Of course, Julia ticks all of those boxes. But additionally, what we need is strong visualizations, developer productivity, and native parallelism. So. If we can parallelize calculations, that's very good in astrodynamics. So more plus points for Julia, I would say. And since I couldn't really decide what am I going to use, I wrote big projects in Fortran, which was, yeah, okay. Since it was Fortran 2008, it wasn't Fortran 77. In the beginning of the year, I decided to do a comparative analysis for an astrodynamics conference. So I took my own micro-benchmarks. So everybody likes to bash them, but at the same time, they're strangely compelling arguments. So what I did was I chose 4 classical astrodynamics problems, so calculating the Keplerian orbital elements. So this is getting information about the shape and the orientation of the orbit in space, solving Kepler's equation, solving Lambert's problem. So this is getting transfers between different points in the solar system. And as I said, legacy code support is important, so calling the DOP 853 Fortran 77 code. And I implement all of those in Fortran 2008, in C++ 14, Java 8, MATLAB, Python, Julia, and got this. So this is lines of code and average runtime relative to Fortran. And oh, this is kind of weak. Okay, there's supposed to be a line here. So this is now green. You don't see it. But basically, being more concise than Fortran. Better? Okay, now whatever, we have to work with imagination. So here is a grid line, and you see being more concise than Fortran is basically the baseline. So the only dot above, this is Java calling Fortran. It's possible, but it's not nice. And so there's also another line here. So when we're in that quadrant, we are about until a factor 10 to Fortran, which is also okay. And what we see here, that most of the languages are at least in the vicinity. So to explain a bit what's happening here, the Python dots actually use number. So also GIT compiled based on LLVM. This one doesn't because it doesn't support closures. Then I think the Julia dots are all quite close, so that's nice. And of course, we have the sad MATLAB corner over here. So if you watch closely, you see that there's one dot missing for MATLAB, which would have been calling Fortran from MATLAB, which is also possible, but I give up. So as I said before, when I got started with Julia, there were some bits and pieces missing which were important. And after finishing my studies and having some time on my hands, I said, okay, now I'm going to learn Julia in earnest. And the first thing, the first package I published was JPL Ephemeris, which takes so-called spice kernels. So this is results from large-scale numerical integrations from JPL, which calculate the position of the planets over hundreds of years. And now I had a possibility to get the position of the planets in full Julia. Next one was Dopri.jl, so again wrapping an integrator, DOP853 and Dopri5, because I needed an integrator with at least 8th order and 8th order Runge-Kutta and continuous output. And those were the main building blocks for my new package, Astrodynamics.jl, which I'm very excited about, but I must confess it's still in a very rough state, and so more Falcon 1 instead of Falcon 9. Probably won't get you into orbit. And what I wanted to do first was get the bread and butter stuff right, which is always annoying, like timescale conversions, vector conversions. Of course, you can do it in Fortran. Just memorize the 6-character ASCII salad procedure, which does it, and the other 5 you need to go from one frame in the tree to another one. And so let's get started with the timescale conversions. On Earth, we're using mostly UTC, which is right here. And if you want to go to TDB, you need to do a lot of conversions on the way. And the problem in astrodynamics is that when you're developing a space mission, the only thing that's constant is that everything changes. So there will be a lot of changes to the requirements, to the specifications, especially in the early phases. And very often the mission design will yeah, go down the toilet because there's no funding. There's a completely different mission flown, so you cannot be too attached to your code, and then writing elaborate Fortran programs is not fun. So, demo time. Okay, we get started with the timescale conversions. Oh, that's bad. It's no fun for you. Can I get the resolution higher?
Just drag one on top of the other. In the picture, the two screens.
What you saying?
It's a mirror already, yeah. No, it doesn't go that high.
Okay. Ooh. Okay, this is... Okay, that's better. Try one more. Okay, here we go. So we start with an epoch, so a point in time, which is now. And now we decide for whatever reason we need atomic time. That works. And we also want to define a new time scale. So we're going to define Helge time, which is by definition 5 minutes past UTC. So we go epoch, Helge time. Okay, and this doesn't work, and it tells me we need a new convert method for that. So let's add it. Same point in time, different time scale, plus 300 seconds. And now it works. So the main difficulty was to get this in multiple dispatch, and I had an idea for that. And I'm still not convinced it's a good one, so maybe have some, if somebody is concerned, please talk to me later. So what I'm doing here is, this is a tree of abstract types. So I'm doing a df search on the type tree, and then if there's no conversion, I get a generated function for that, and so I can do multi-step conversions. It's not stupid when it works. Okay, same for state vector conversions. So this is a state vector for the ISS, so we need a position vector, we need a velocity vector, and an epoch. Here we go. And now we can also do all sorts of conversions. You see this one has 3 type parameters. This is the coordinate frame, so this is the geocentric celestial reference frame, which is an inertial frame based on well, I think extragalactic radio sources. The timescale and the central body. And now we can say what is the state vector in a rotating frame. Or what's the position of the ISS in relation to Mars? In a Martian reference frame. And of course, they have Helge time on Mars. So now we have timescales, we have state vectors, and we can do something with it. So like projecting, propagating into the future. So for example, by solving Kepler's equation. Unfortunately, embedding stopped working, but takes a bit longer, but looks nice nevertheless. And we have the orbit of the ISS. So, but this is since this is just the two-body problem, so an approximation. We actually need a better force model to get closer to reality. So now we can do the same with numerical integration. Or we could also, so this would be for a spherical Earth, which is not true. It's an oblate spheroid, so more like an orange. And if we consider that, we see that the plane of the orbit actually starts turning. Starts precessing.
No, it's just because it's an oblate spheroid.
Yep. And again, Julia is really helpful here. So because I just defined a new type for that, so there's an abstract model type, and when I decide to go even deeper and have instead of one coefficient, have 40 or 1,000 for the gravity field of the Earth, I can do that at any time without needing to change code. So let's get discontinuous. So at maneuvers. As you probably know, the ISS is in a very low orbit and needs to be pushed every few months, I think. And so what we do now is we add a maneuver, which is a discontinuity. We apply the thrust at the pericenter, so at the point closest to Earth, and we use a delta V, a velocity difference of 100 meters per second. And that worked. So you see we boosted the orbit. We could also crash it. Yep, that worked.
So you can define an impact error.
Yep, exactly. So there's 3 different kinds of events. There's like transient events, which don't do anything, like eclipses or just detecting certain points in the orbit. Then there's discontinuities where the state vector actually changes, and then we have abort events like this RUD, which is a rapid unscheduled disassembly. So as I said, astrodynamicists are a conservative bunch, and since it is my opinion that all of us astrodynamicists, which should be a little bit more like Elon Musk, I'm going to show you something new. And I have to change branches for that, and it might break. So what we want to do now is optimization of the orbit. We start with a new state vector. Let's see if that worked. Okay, so this is the semi-major axis is 7,000 kilometers. It's almost circular. And what we want to do now is to go to a higher circular orbit. So we need two maneuvers for that. One is the raising of the epicenter. So you arrive at the point closest to the Earth, and then you turn the circle into an ellipse. And when you then arrive at the point farthest away from the Earth, you raise the pericenter, so you circularize the orbit again. So you need two maneuvers for that. And this is the first time I used Julia metaprogramming. So actually, for the impulsive maneuvers, these are not Julia floats, they're parameters. And this macro is kind of a syntactic sugar for entering those. So I'm saying this is the delta V for the epicenter raising. The initial value is 1 times 10 to the power of minus 4. The lower bound is 0, the upper bound is 4 kilometers per second. And then it takes it from here, replaces it with a parameter type, which looks like this. And then those parameters are directly available to the optimizer. So again, we need an integrator with the two maneuvers. And what I started here is the modeling of a mission. So in the end, the mission is supposed to consist of several segments. So like in different spheres of influence, so you start at the Earth, go to deep space, go to the moon, and then you have patch points where you have to connect the trajectories from there. And so this is a very early prototype of that. And here we have the boundary conditions. We start with an initial orbit with a state object. And we stop at a target orbit with a semi-major axis of 42,000 kilometers and an eccentricity of 0, which means it's a circular orbit. And then we plug that into the optimizer. And now for something completely different. This code is based on a new package which is called Spice.jl. And it's a wrapper for the Spice library from JPL, which has a lot of auxiliary functions for astrodynamics. And I'm using it for visualizing the target orbit. which looks like this. You see something? Yeah, good. Okay, that's it for the demo. So to conclude my talk, just one more remark. As I said, Fortran in Europe and in parts of Europe and in the US and in France there's Java and many people are C++. They have a they're very strong in Astrodynamics. So and if we as a community want to have a chance to offer an alternative, the most important thing, unfortunately, is just this one, I think. But as Stefan said this morning, it's getting closer, and I think there's a bright future for Julia in space. So, thank you very much.